So we got a few more things to clear up about these second order equations. If you'll recall, our strategy was to look at this second order equation with constant coefficients and just guess that y is equal to e to the k times t. This led to the characteristic polynomial. Now I'm going to put equation of k squared plus bk plus c equals 0. And then this led to our three different cases where we had distinct real zeros, real solutions. I wrote the equation, so I have to say solutions. We could have a repeated real solution. Or we could have complex conjugate solutions. It's quadratic, so we have to have two solutions. The differential equation is second order, so we have to have two linearly independent solutions. In the case of distinct real solutions, our general solution was y is c1 e to the k1 times t plus c2 e to the k2 times t. That was what we used in the distinct real solutions case. In the repeated real solutions, I couldn't just put e to the kt and then e to the kt. I would just combine those two into just e to the kt, because they would be linear combination. One would be a linear combination of the others. So in the case of repeated real solutions, we just use e to the kt and t e to the kt. And mysteriously, that seemed to work just fine. So I have a c1 e to the kt and a c2 t e to the kt. I'm going to factor it out to make sure it looks different than the others. So this is what happens if k is a solution to the characteristic equation and k has multiplicity 2. The other is complex conjugate solutions. Now we started off with just pure imaginary. We looked at y double prime plus 9y equals 0. And we said we're looking for a function whose second derivative is a like term with the original function. And that made us think of trig functions, sine and cosine. But what if the complex conjugate solutions are complex with a real part and an imaginary part? So if we have complex conjugate solutions, say k equals a, shouldn't use a, no, I'm just going to use a and b anyway, a plus or minus bi. So yesterday we looked at the case where we just had plus or minus bi. So k was plus or minus 3i. But what if there's some constant, some real parts, a? So then we make our general solution. We have a c1 cosine of bt plus c2 sine of bt. Now this is if we have a equals 0. If a is not 0, then instead of getting this oscillation, just sines and cosines, we get an e to the at. So This is just me telling you what you need to write and regretting not giving myself enough space to write it. So e to the AT is just like shoved up in there. Let's look at an example. So let's suppose we have y double prime. I need to make a quadratic with complex conjugate solutions or complex conjugate zeros. So y double prime, I want a to be negative. So we'll go plus 4y prime plus 13y equals 0. We make the same guess that we did before, e to the kt. And then this leads to the characteristic equation, k squared plus 4k plus 13 equals 0. And then we skip the quadratic formula because the quadratic formula is lame. And we rewrite this as k plus 2 squared plus 9 equals 0. So we complete the square. K squared plus 4k, I need a plus 4 to make a k plus 2 squared. And that, take the 4 off 13, that leaves a 9. So our solutions, k is going to be negative 2 plus or minus 3i. Got a quadratic with real coefficients, has two complex zeros. In this case, they are in fact complex. Negative 2 plus or minus 3i. They have imaginary and real parts. So the general solution, to incorporate complex conjugate solutions into a general solution, we write factor out an e to the negative 2t. And then we'll have a c1 cosine of 3t plus c2 sine of 3t. All right. So why is this working this way? Let's take a look at a tool that we have in the toolbox. We know that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. Let's think about what e to the I times t looks like. Let's look at what happens if we plug in an imaginary number into e to the I, into e to the x. So let's look at e to the I times, I spelled I wrong. So I'm going to replace all the x's with just I times t. So 1 plus it plus it squared over 2 factorial plus it cubed over 3 factorial plus it to the 4th over 4 factorial. I'm going to do one more. Plus it, just for balance, to the 5th over 5 factorial, and so on. Remember that all powers of I are either 1, I, -1, or -I. So recall, I to the 0 is equal to 1. I to the first is equal to I squared is -1. I cubed is -I. Then when we get the fourth power, we're back to the beginning. So this is also I to the fourth. I to the fifth is just I to the first, which is I to the sixth is -1. I to the seventh is -I. And so I to the eighth, we're back at 1 again. Powers of I are just plus or minus 1 or plus or minus I. So let's see what happens here. Some of these are going to leave an I, but some of the I's will get changed. So I'll have 1. Let's see. Let's write down what we have. We got 1. This IT is going to stay IT. It's I to the first. So I just get IT. But this second one, this next term, oops, I spelled exclamation point wrong. There. Get a comic book exclamation point. But the second one has an I squared. I squared is equal to -1. So I have a minus t squared over 2 factorial. The next term has an I cubed, and I cubed is just -I. So this is going to be, I'll still have a t cubed and a 3 factorial. But I cubed is -I. In the next term, I have an I to the fourth, and I to the fourth is equal to 1. In the next term, I've got an I to the fifth. I to the fifth is just equal to I. And I have t to the fifth over 5 factorial. So if we look at how things are being separated, I've got a real part and an imaginary part. I've got a real part with 1 minus t squared over 2 factorial plus t to the fourth over 4 factorial. All the even-powered ones are going to be real. That's the real part. So I'm going to have, if I gather up my terms, I've got a 1 minus t squared over 2 factorial plus t to the fourth over 4 factorial, and so on. And then I have this imaginary part. All the odd ones have a factor of I. So I'm going to have I times t minus I times t cubed over 3 factorial plus t to the I times t to the fifth over 5 factorial. Oh, and these are all multiplied by I. Now, if we notice that the real part of e to the it is cosine of t. The imaginary part of e to the it is the odd one. It's sine. So this is plus I times the sine of t. So knowing that e to the it is cosine of t plus I times the sine of t, we can adapt this to e to the a plus b I have to write it first. A plus bi times t. I can separate out an e to the at, and I multiply by e to the bi times t. E to the at will just keep as e to the at. Oops, not times, not equals. And the e to the bi times t is just going to be the cosine of bt plus I times the sine of bt. And so now we've stumbled upon Euler's formula. So we end up with these complex numbers. We never think they're going to be useful. We call them imaginary. It's like, oh, these are just imaginary numbers. Really, we're just naming stuff. And since the names for the amount of things are just like the numbers are just names for amounts that we came up with and all agreed on. Like this is 2 pens because there's 2 of them. And we've just decided to call this quantity 2. So from that standpoint, this is all imaginary because we're just using words to describe things. We just happen to agree. So these imaginary numbers, when we're looking at these quadratic equations, say, well, this is unsatisfying to not have solutions to these quadratic equations. It's unsatisfying to have numbers that only square to positive numbers. Let's invent some whose numbers whose square is a negative number. Like I was there. And so we stumble across Euler's formula, and we see this strong relationship between these cosines and sines and the e to the x function. It's handy that this comes up after power series and Taylor series, because we have the Taylor series for e to the x. All right. Euler's formula, in case you're concerned, is an important thing. I will drop a link to, this is how you can tell something's important. It has a Wikipedia entry. I know as an academic, I'm not supposed to tell you to go to Wikipedia, but if ever you find something on Wikipedia and you got one of them professors that's like, oh, don't use Wikipedia as a source. All the sources for Wikipedia are listed at the bottom. So whatever part of the Wikipedia you use, just reference the part at the bottom. They tell you where they got this stuff from. There's where your footnotes are. Don't be like, oh, I got this from Wikipedia. Then they're gonna be like, oh, that's no good. But if you got it from Richard Feynman, the Feynman Lectures on Physics, Volume 1, Addison Wesley, with an ISBN no less, then you'll sound fancy and sophisticated. You know what I mean?
Professor, I have a question.
Yeah.
What would we use Euler's formula to solve for?
We need it for these kinds of differential equations. So where we could get these kinds of equations from, let's suppose, here's something that we know. Acceleration due to gravity is constant. We know acceleration due to gravity is constant. We also know force is mass times acceleration. We also know that wind resistance is a thing. Oh, maybe I should say air resistance. Is it resistance or ence? When in doubt, abbreviate. So we need an idea about how to describe wind resistance. One thing that we notice about wind resistance is that wind resistance seems to increase with speed. The faster you go, the more the air is pushing back on you. That's why when you stick your hand out the window of a car, don't do that because you'll lose a hand that way. But you stick your hand out the window and hold it flat. The faster you go, the more the wind is pushing on your hand. So maybe we come up with some idea that wind resistance is proportional to velocity. So we get force is mass times acceleration, and wind resistance is proportional to the velocity. And that's a force too. Acceleration due to gravity is constant. Force is mass times acceleration. Acceleration is a second derivative. So one of the forces that we can build is a constant times a second derivative. Another force that we can build is proportional to the velocity, which is a first derivative. Acceleration is a second derivative. Velocity is a first derivative. So now it's conceivable that we have an equation involving a second derivative and a first derivative with constant coefficients. That means we need to understand all the solutions to this equation. We need to understand all the solutions to this equation. And that means we need to understand how the complex conjugates show up in the general solution. So Euler's formula to the rescue. Because we know that this equation leads to that polynomial equation. So we need to take into account everything that can happen in this polynomial equation. That includes complex conjugate solutions. That includes Euler's formula.
Got it. Thank you.
As far as us personally, these are all problems that are well known and well understood. So I don't know what we're going to be doing with this moving forward. But we do need to understand where we've been. Here's a fun part. If we have, let's say we have a differential equation. Let's say we have a third order equation. And let's say it leads to a characteristic polynomial that has, let's say, k minus 2 times k minus 5 squared. This is something that could happen. If a third order equation will lead to a third degree polynomial solution, and so we have a 2 and a 5 and a 5. So our solutions are 2 and 5 and 5. 5 has multiplicity of 2. I should make this a 3 so that we're not messing around with the 2's. Do a little prime number shift. To build the general solution, I need a C1 e to the 3t. Then I need to do two 5s. So I'll have a C2 plus C3t e to the 5t. If I have a fifth order equation, and I'm able to look at the structure of the characteristic polynomial, and there's a k minus 3, and then a k minus 5 squared, and then also a k squared, what did I use? Plus 2k plus 13 equals 0. Here are my 5 solutions. I got 3, 5, 5, and then 2 plus 3i and 2 minus 3i. So my general solution, I would not want to be finding the constants in this one because there's going to be 5 of them. But I need a C1 e to the 3t. I need to deal with this 5 showing up twice. So I have a C2 plus C3t e to the 5t. Plus, and then the solutions here are 2 plus or minus 3i. So I'll also need an e to the negative 2t times C4 cosine of 3t plus C5 sine of 3t. So we can just take what we know about the quadratics and just build it out. Let's suppose, go one more example, and then we've got this whole thing covered. Let's suppose that we had a fourth order equation where we had our characteristic polynomial was k plus 1 to the third times k minus 3. So now my solutions are -1, -1, -1, and 3. Because -1 has multiplicity 3. I shouldn't use 3. What the heck, man? Let's make that a 5. -1 has multiplicity 3, and then I have a solution of 5 multiplicity 1. I keep saying solution, so I better write an equation. To write my general solution, I need to take into account 3 different e to the negative t's. So I'll have a C1 plus C2t. That's how we dealt with multiplicity 2. I'll give you a second to guess what we're going to do with that multiplicity 3 one. Everybody ready? Wait for it. If you guessed we just put on another t, then you are correct. That's just how we deal with multiplicities. We add extra factors of t. My dog is concerned that we're going to have to solve for all these constants. We're not going to have to solve for all these constants, but it's all good. That sounds like busy work, Dad. All right. That's going to do it for today. That's going to do it for this week. Keep an eye out for the last couple of quizzes that need to show up, and keep working on fixing things. Remember, some of the quizzes, you lose access on the 21st. So those are the ones that have been up for months, so I don't actually feel bad about that. But some of the quizzes you don't lose access to until the very end, which is the 28th, at which point you lose access to everything in the class. So make sure you're all done by then. If you put it off to the 27th and then run out of time, I'm not really going to feel bad. So if I see you haven't done any homework and then you're all going to try to do it all in the last week, I'm not going to feel bad if you don't get it all done. So we've only had 17 weeks to do 18 weeks to do some of these things. So, well, we haven't had 18 weeks to do some of them, but we've had a lot of time to do these things. And keep in mind, this is much better to have weeks to do something than like 2.5 hours. But then again, maybe since I'm late because my commute is 10 feet instead of like 5 miles or 15 miles, maybe that's why we are going to be putting things off. You have a whole month to do the thing, and so you're not going to give yourself enough lead time. I've doomed you all. Anyway, that's it for this week. That's it for today. That's it for this week. Everybody have a good weekend, and thanks for playing.